want that you refresh. You remember that table in the book of electricity? Is what? About what? About the level of energy of each element. Each element by itself have your own level of energy. You remember that in some cases when you check the hand of other person, you feel electricity in some cases? It's because that person is more charged than you, or you more charged than him, no? And when you connect both hands, the hand with higher energy drain energy into the other one, no? Okay. Each metal by itself have your own level of energy. How much is the level of energy of aluminum by itself? Aluminum, 1.5 millivolts. Well, how much is the level of energy of iron by itself? 1.8. How much is the level of energy of magnesium? 1. Yeah, each element have your own level of energy. Pay attention. If I put together, for example, I am going to put together copper and aluminum. Copper and aluminum are recommended together in a marine environment? No, never. Okay, what happens if I have an aluminum tank and I install fittings of copper? How much is the energy of copper? 1.9. And aluminum? 1.5. Which one attack the other one? Copper to aluminum. Which one donate electrons to the other one? Aluminum. Which one will be eroded? Aluminum. For that reason, what happened around the fitting in that area of the aluminum?
It was eroded.
And suddenly one of those, and you have a hole over there. Yeah, now you understand? Pay attention. The outboard, the frame of the outboard is aluminum. 95% is aluminum. And a couple of balls in steel. Iron alloy. Let me check that. Aluminum and iron. Which one have more energy? Iron. Oh, the balls. What happened with the aluminum around the balls in an outboard? Correct. That area around the balls is eroded. It's easy after 3 years remove those balls. Suzuki outboard have a lot of problems, say Danny. It's because the quality of the hardware of the stainless steel. The balls are stainless steel, but not the best stainless steel, and produce a lot of corrosion in between the aluminum and the hardware. You know? Okay. There are a lot of examples. For example, pay attention. Pay attention. Simple. I have an aluminum hull. Aluminum hull. And I want to protect. You remember that there are 3 types of anodes. We are going to talk later about that with more details. Sacrificial anodes in zinc. Sacrificial anodes in magnesium. You remember magnesium? Because magnesium have 2 electrons in the last orbit. You remember, guys? Sacrificial anodes in zinc, because zinc also have 2 electrons in the last orbit. And there are sacrificial anodes in aluminum alloys. Aluminum alloys. Those are alloys of aluminum mixed with other element with 2 electrons in the last orbit. Because aluminum by itself is not a good sacrificial anode. The aluminum should be combined with other ingredients to be attractive for the oxygen. That ingredient is cadmium. It's an alloy of aluminum with some amount of cadmium. The sacrificial anodes of aluminum is not pure aluminum. It's aluminum with cadmium. Yeah? All right. Cadmium and other ingredients. Okay, pay attention. I have a boat in aluminum. what happens if I install sacrificial anodes of zinc in that boat? Is a good protection? Let me check. Aluminum, the level of energy, 1.5. The zinc, the level of energy. Can the zinc protect my boat in aluminum? No, no. In that case, my boat is the sacrificial anode. Yes, my friends, all of those selections depend on the level of energy of each one. Pay attention. In this particular case, what about magnesium? The level of energy of magnesium? 1.2. Oh, magnesium is more anodic than zinc. Zinc is 1.6. Yeah, in some cases, the aluminum alloy, aluminum mixed with the cadmium and other ingredients, the level of energy is pretty close to 1.2, 1.27. That's great. It's a good protector. In that case, my aluminum boat will be protected better with the aluminum alloy sacrificial anodes. Yeah? Oh, if my aluminum boat will be running in fresh water, in lakes, the sacrificial anodes excellent are in magnesium. Later we are going to talk about that. The selection of the metals is the secret. You always hear that the people say, okay, install zinc to protect that. Install zinc. In an aluminum boat, zinc is not good. No, because zinc is good for salt water. Yes, zinc is good for salt water. But with aluminum, no. Doesn't matter if it's in salt water or fresh water. That's clear, my friends? The selection of the metals is critical. The same with the hardware. This is one point where the people not pay attention. Is where is coming? That hardware is perfect stainless steel. Is perfect marine grade stainless steel. No, it's a stainless steel now. If it's a stainless steel but it's not marine grade, it's not good for your boat. No, but it's a little magnetic. It's practically nothing. That's not good. Yeah, should be marine grade. Today we are going to learn what are the alloys, ferrous alloys allowed in the marine industry. What are the non-ferrous alloys allowed in the marine industry? Not all the non-ferrous alloys are good. There are non-ferrous alloys not approved for marine environment. Basically because the level of zinc mixed in the alloy. All right? There are two types of metallic boats. Aluminum boats and steel boats. Big cargo ships, they are in steel. But in those boats, the type of protection is not with sacrificial anodes. It's with the impregnate current, the EPC. We are going to learn that process. That process is too simple. You know what happened when one element complete an electron in the last orbit? It's stable. What is the meaning of that? No react, because it's full. It's full. When you eat a lot of chicken and hamburger, what happened in 2 hours? You want a banana? You say, no, I am saturated. I am full. No? This is that system. If you have a metallic boat and you bombardier the structure with electrons and you saturate the boat with electrons, it's possible that the oxygen attack that boat? No, because it's saturated. This is the idea with the IPC, impregnate current cathodic protection. It's saturation of electrons, it's full, and it's not corroded. It's nice. This is the last chapter of this class. This class will be nice. Follow the videos. Check the book. My friend, the book is nice. Check the book. You see the first chapter? It's good information, but the next coming chapters are better. The majority of the metals used in the industry, in naval, in automotive, in aviation, are located in this group. What is the name of that group?
Transition.
Transition metals. Transition metals. Those elements located over there in that group, they are excellent conductors of electricity, excellent conductors of temperature, excellent conductors of heat. Yeah? Those elements located in this section, transition metals, are excellent conductors. Temperature, electricity, heat. And those are the elements that normally are used in different type of reactions. Okay, we are going to use a lot of iron, nickel, copper, zinc, magnesium. All of those are used in the industry. Okay, my friends. Remember that small group, zinc, cadmium, and mercury, they have only 2 electrons in the last orbit. The rest of those elements, they work with 3 electrons in the last orbit. The oxygen prefer attack those elements because it's easy, no? The same that the elements located in this group, in the orange, they have 2 electrons in the last orbit. What is the inconvenience with those metals? All of them except one. They have one inconvenience. Why I don't use all of those like sacrificial anodes? They have 2 electrons in the last orbit.
Water.
They react with water, except magnesium. Magnesium not react with water. The rest of them, yes. For that reason, to create sacrificial anodes, basically I have 2 options. One option is zinc. It's cheap. You find a lot of zinc in the market, in the world. What about cadmium and mercury? They are poison. What about mercury? It's poison and it's liquid. That's not good. The other option is magnesium. The rest of the metals here, they react with water. Yeah, they produce a spark, they produce explosion. No? It's no good. Magnesium is a great choice. For that reason, we are going to use sacrificial anodes in magnesium, especially if the boat is running in fresh water. In fresh water, magnesium is the best option. Okay. Okay, you remember properties of iron? Iron is magic, no? Why? It's magnetic. Other great property of iron
Back to original form.
Abundant.
is
Strong.
the strongest. Which one? What other one?
It doesn't make it go back to its original form.
Correct. Good. Good memory. You deformate the iron, and the iron return to the original position. The elastic area of the iron is a big area. No. Other good property of iron, very important. It's cheap. It's cheap. For that reason, everything is fabricated in iron because it's cheap. No? And the most important property of iron is magnetic. Because iron is that we have electricity. Remember that electricity is produced for the generators, no? The electromagnets spinning around the coil. That's because the magnet is that we have electricity and we have computers and we have everything. Without iron, that's not possible. Iron is magic. You have another metal in the periodic table with those properties, magnetic properties? No. That's the unique. Okay. How can you inhibit those magnetic properties of iron? When you added what? You need added in the alloy iron plus, excuse me? Chromium! Chromium! Around how much amount of chromium maximum? 18%. 18%. Ah, stainless steel. Stainless steel, if you check with the magnet, doesn't have magnetic properties. It's because that alloy have high content of chromium. there is another metal that inhibit the corrosive, the magnetic properties. Chromium is one. What is the other one? Nickel. Both of them inhibit magnetic properties and corrosive properties, both of them. Because stainless steel is zero magnet, zero magnetic, and practically zero corrosive. It's because the amount of chromium and nickel. Okay, this is in ferrous alloys. Alloys based on iron. In non-ferrous alloys, alloys based in other metals different than iron, the element that inhibits the corrosive properties of that alloy is nickel. Yeah? No chromium. Chromium is not common in non-ferrous alloys. Chromium is very, very common in ferrous alloys, especially to create proper stainless steel. In non-ferrous alloy, you reduce the corrosive properties with nickel. Yeah? Nickel will be in both. But in non-ferrous alloys is the best to inhibit corrosive properties. Other magic element is carbon. But carbon have one inconvenience. What is the inconvenience of carbon? Where is located? Where is located? Here is the division. Metals and non-metals. What happened with carbon? Is in between, in the limit. Carbon in some moments is metal. In some moments is non-metal. Oh wow. Depend of what?
Heat.
The temperature. Oh nice. Oh, if I have a boat in carbon fiber, what happened in the summer with that boat here in Florida? That boat is a metallic boat. The structure is metallic. What happened with that boat at north during the winter? It's a non-metal. It's like a fiberglass carbon. Yeah, it's an structure non-metallic. Depending of the temperature, works like metal or non-metal. For that reason, in those type of boats, the bonding should be designed perfect to avoid that you drain currents into the structure, to avoid that electrical and electronic devices touch the structure directly, because the structure in some cases is metallic. You know, you need to be careful when you install electronic devices in those carbon fiber boats directly into the carbon fiber. That's not good. You need to install pieces of cardboard, wood, and over there you install the electronic devices. You need to isolate the structure. Carbon have that inconvenience.
They use
But-
fiber. They use fiber washers. Or they use
Oh
rubber
yeah,
washers.
plastic, something like this. Yeah, but excuse me. Other great property of carbon. Carbon is magic. Exactly the same like iron. You know that carbon, depending how you put together the atoms of carbon, you have diamonds. Wow, you have diamonds. You have a special tools, cutting tools in diamond. But also, depending how you put together the molecules of carbon, you have graphite, and graphite is a perfect lubricant. But it's carbon. You have lubricant, or you have diamonds. It's incredible, no? And it's the same carbon, graphite. No? This is a magic property of carbon. Carbon is incredible. The enemy of the carbon presentation is the temperature. When the temperature increase, become metal. In some cases, will be no good, no? Depending of the situation. This is carbon. Carbon is another. What is the technical name for carbon, silica, and germanium? Those three elements. Semiconductors. Semiconductors. They are used in electronics to create circuit boards. You remember? What is the enemy of the circuit boards? The temperature. For that reason, in all the computers, in front of the circuit board, you have what? A fan. For that reason, say to your wife, say to your daughters, don't use the laptop on the bed. Don't sleep with the laptop, because you damage the circuit board for temperature. Yeah? The temperature is the enemy. Okay, those are properties of carbon, silica, and germanium. Properties of copper. Copper is excellent. Is in those three elements, copper, silver, and gold, are the best conductors of electricity. Copper, silver, and gold. The best conductors of electricity. Incredible, no? What is the inconvenience with the silver and gold? Can I create all the wires in my boat in silver and gold?
Sure, yeah.
If you have the money, yes.
You're stealing wires.
Yeah. Oh, of course. Those are perfect conductors of electricity. Copper is a little less conductor. It's good. Those are perfect, but too expensive. For that reason, we use for wires, for cables, copper. Because it's good, it's a little cheaper. No, it's a lot cheaper in comparison with silver and gold. All right? But those three elements, they have similar properties. And you remember externally gold and externally copper, they are pretty similar, no? The color of gold, the color of copper, when you polish the copper and you polish the gold, is practically the same. Yes or not?
Yeah.
You remember? It's practically the same. Some people confuse copper with the gold. And internally in the structure, they are pretty similar. The only difference is that in the previous, not the last orbit, in the previous orbit, in the previous one, copper have one more electron than gold in that orbit. For that reason, a lot of scientists years ago, they tried to remove that electron from that orbit in order to convert copper in gold. Some years ago, some scientists, the name of those scientists are the alchemists. You remember? They say to the king, "Hey, Mr. King, we have the formula to convert that amount of copper in gold." "Oh, really, guys?" "Yes. We need money to create an equipment, and special equipment is expensive, and we introduce copper on top, and in the bottom you have gold." "Hey, Papi, how much money you need?" "No, we need some, And the king gave money to them, and they start to fabricate that equipment to convert copper in gold. That was 5 centuries ago. And they can't. It was impossible for them. But some years ago, in the previous century, in Berkeley, in California, some students of a doctoral degree in chemistry, they create the machine. It's a centrifugal machine, and they excitize the previous orbit, and they send out for centrifugal force that electron and convert copper in gold. The problem is that the amount of money and energy that you need in that machine to convert 1 pound of copper in gold is too much. Practically the price of the copper, of the gold. Yes, it's possible, but it's too expensive. You can convert copper in gold. You can remove that electron, but it's too expensive. It's demonstrated in Berkeley. They did that. Okay, good. Let me check a lot of ferrous alloys and non-ferrous alloys for the marine industry. What is the inconvenience with brass? What is the inconvenience with brass? A lot of
Corrosion.
a lot of zinc, in that alloy. For that reason, that alloy is non-marine grade. It's not approved in the marine industry because the amount of zinc, and because produced too much. How you pronounce?
Dezinkification.
Too much for me.
Just what he said.
Yeah. Exactly like you said. All right, what about bronze? 90% copper and tin. It's good for propellers. Excellent for propellers. Bronze, naval bronze. What about duraluminum? Where is used that alloy? Where is used that alloy?
Airplanes.
In aviation, in airplanes. This is perfect. Duraluminum, copper, magnesium, aluminum. It's a great alloy. The aviation industry is divided before the scientific discovered duraluminum and after. Before of that alloy, the majority of the structures in airplanes are in wood, different type of wood. After the discovery of the duraluminum, the aviation industry, wow, grows dramatically. It's perfect. It's not used in marine application because the amount of copper. Okay, solder, tin and lead is used. Monel, 400 and 500. Look at this. Where you found that monel? You remember in intro?
Shafts.
In the fabrication of the shafts. You remember the propeller shafts? Okay, that material to fabricate the shafts is the same material used in the oil industry, in the perforation to suction of oil, because of those shafts are attacked with acids. That alloy, Monel 400 and 500, is used in the Gulf of Mexico in the oil industries. This is a great alloy. Look at the level of nickel. It's more nickel than copper. Those shafts are fabricated practically 70% nickel. It's a lot. 30% of copper and a little silica. What is silica? Sand. No? Is nickel. You remember what is the element that inhibits the corrosive properties in non-ferrous alloys? Nickel. Can you corrode those shaft propellers? No, it's zero corrosive because that amount of nickel is a lot. This is Monel. Which one is the other one? Oh, Nibral. You remember Nibral? The propellers. The propeller is a nickel, copper, aluminum, magnesium. This is a great alloy. It's hard. Aluminum alloys. There are three types of series, or two types. 6,000 and 7,000 series. 6,000, look at this. The aluminum 6,000 series, 95% is pure aluminum, and the rest is silica and magnesium. This is highly used in marine applications. And the series 7,000 is 97% aluminum, a little amount of zinc and silica. Less used in marine application. The most common is the series 6,000. Okay? For that reason, when you order the fabrication of brackets, aluminum tanks, ask for the guy, my friend, I want the aluminum series 6,000, not 7,000. Because the 7,000 have zinc, and soon or later will be corroded. The series 6,000 is excellent for marine application. Okay, guys? Molmax is another great alloy used in marine application. It's 97% of copper, nickel, beryllium. It's high strength, good thermal conductor, good wear resistance, and it's easy to weld. This is another alloy commonly used to fabricate a lot of, for example, the material for the swim platform, Mol Max. Nice, no? Naval bronze. You hear about naval bronze. It's 85% of copper, tin, lead, and a little amount of zinc. And babbitt. You remember babbitt? Where you found that babbitt?
The bearings.
The bearings. You remember the bearings of the crankshaft and the camshaft? Yeah, this is the composition of the bearings. Okay, now we are going to talk about ferrous alloys. Ferrous alloys. Those are alloys based on iron, 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 iron. And look at the most common alloys. The series 316. 316. Why 16?
The percentage?
It's because the amount of chromium is in between 16 and 18% of chromium. And look at the nickel and iron. It's good for atmospheric corrosion, pollution. Stainless steel series 304. This is the composition. Those alloys, my friends, those alloys are marine grade alloys. What is the meaning of the letter L? Low level of carbon. Low level of carbon. Low level of carbon. And look at those other marine grade alloys. You need to be familiarized with those series. 316, 304, or 18A or 1810. Let me explain what is the meaning of 18A and 1810. 18 chromium and 8 of nickel. 18 chromium and 10 of nickel. And the rest, iron. You see? You remember that I said at the beginning, if you have chromium, you inhibit magnetic properties. If you added nickel, you inhibit corrosive properties. If you added both of them, you have the perfect scenario. How much should be the composition of each one? No more than 18% of chromium, and nickel in between 8% or 10%. Yeah, those are the most famous 18A or 1810. Which one is a little more sophisticated, 18A or 1810? 1810 is more expensive. Yeah? For that reason, some people say, oh, all the brackets, all the structures, the motor mounts for the support for the motor mounts in my boat are in a aluminum grade, marine grade 1810. Oh, it's expensive. And the welding area is with rods in 1810. No? And the welder that apply the metal is a marine welder. If you added more than 20% of chromium, the alloy become too fragile. It's fractured easily.
Brittle.
It's brittle.
Brittle. Thank you. That's the consequence. Yeah, it's difficult control the amount of chromium during the cast, but today it's with computers. They added exactly the amount of powders of chromium, exactly like the machines designed to prepare paints. No, you go with the color that you wanted, and they added exactly the amount, and the color is perfect. Today, in the foundry industry, they have computerized everything. That situation. But more than 18, that's not good. That's damage the alloy. Okay, those famous alloys: Aqualloy 17, Aqualloy 19, Aqualloy 72, 22. Those alloys are used in the fabrication of shafts for propellers, shafts for propellers of inboard and outboard engines, both of them. This is the main use. The letter L is for a low level of carbon. Okay, don't forget that. Those are the most common marine ferrous alloys.